I'm going to talk about who are we very quickly, and the challenge of isolation and integration and high density problems. And you all know this stuff, so I'll be very quick. We're going to illustrate the points with how we've approached a W-band converter design. Then we're going to talk about some gasket and absorber technology we offer, and then move into real-world examples with our products, switch matrix and frequency converters. And we're going to talk about our current contract with Airbus OneWeb and Ramon Space. So cool. So just a couple of minutes about us. So we're in year 9, RF and microwave products company, space, defense, commercial, quantum computing. We do everything with an RF and microwave flavor, but it doesn't just include, it's not just consultancy. We do manufacture, product design, sell products, help with testing. We have now a class 7 clean room, class 8 test and measurement lab. We're fully loaded with all the kit we could need. We are now involved in space product assurance, EMC, mechanical, thermal. We can even conduct like a radiation test campaign. Previous projects we've been involved in, Airbus OneWeb, all sorts of various space missions, and we're a growing team of capable engineers, and we've completed 40 plus projects now, ranging from 10K to £1 million. So over the last 8 years, we've delivered 19 flight modules. We've delivered the world's first GPS system that is flying to the moon next year. We've delivered 9 payloads for remote sensing, GPS reflectometry. This is actually launching on Monday, Monday night. So those are the modules there. All of these 9 modules are going up on SpaceX on Monday. We provided a payload to the ISS that's up there working. And we also delivered an ultra low noise X-band frequency low noise block, which actually went up on last Saturday, and I heard today actually that it's working okay. So, and that's the launch there. So that was taken last Saturday. And here we've got here I've got radiation testing, and this is our team delivering the SSTL lunar hardware. So that's the hardware we built there. So we've invested heavily in equipment and personnel. So we've got wire bonding capability, BGA rework stations, thermal chambers, clean room, ANSYS simulation, so everything, all the microscopes and high-end soldering kit you would need. We also offer this as a service should you need anything like this. And so onto the subject matter. This one is just going to be quite quick here, because this is just setting the scene of the topic of the talk. So essentially, there's currently unprecedented demand. Market drivers, 5G, 6G, advanced communications, high-speed defense applications. Everybody's wanting to pack RF in smaller and smaller spaces, but increase the complexity of it. And so maximal integration across all sectors. So a proof of point, Airbus OneWeb, they're building the next generation of digital payloads. We have the contract to do all the environmental test campaign for it. And that demonstrates really our capability to handle complex integrated systems, and the complexity of this payload is unprecedented, really. So obviously, just to say that as you try and compact everything very small, the performance goes down. Just a simple graph there showing the higher the frequency, the more the coupling, the more the distance needs to be. So we've got significant design challenges to obtain isolations here. Critical failure modes are always port-to-port cross-talk, cavity resonant modes, things might oscillate, and everything degrades. So gain flatness, efficiency, return losses, it all changes as you try and squash everything down. And moving in the higher frequency range as well, we've got a lot more of the frequency bands are opening up around the 71 to 75 gigahertz, in the SATCOMs, the telecoms. And so the real challenge in designing all of this hardware all the way up to 100 gigahertz is 3 things. You've got to maintain the signal integrity, so you need precision shielding, mitigating crosstalk, coupling, and in tightly packed layouts, everything needs to be controlled. Thermal management, packing it in, everything gets hot. And finally, when you want to mass produce this stuff, the yield is really hard to keep repeatable performance, ripple, matching, return loss, repeatable results, and the thermal balance. So these are the key challenges I'm going to talk about here. So the way I'm going to talk about it is with reference to a project we've just completed. So I think that's a bit easier. We were contracted to deliver a tester system for a company to measure W-band automotive chips in the tens of thousands. The chip has 4 inputs, 4 outputs, but they needed to do it in a very cheap way. So they have conventional kit that works 2 to 6 gigahertz. How are we going to allow that kit to test automotive radar chips at W-band? So we have current product with Ka-band extender. We developed a new product, a W-band extender, and we developed a waveguide to allow us to split the signals and get them into a little BGA. So I'm going to basically talk briefly about all of these components as an example to how we do things. So this is the system we came up with. We've got here, this is a tray, go back, this is a tester, or commercial tester. They cost a couple of £1 million. The tray that goes in it, this is our, if I go back, this is our Ka-band extender. So this takes our 2 to 6 gigahertz, mixes it up and down, up to 27 gigahertz. We've got that, then got our W-band extender that takes 27 gigahertz up to W-band through 3D printed waveguide that we've had made, and essentially input, output, and it splits it inside the waveguide using this topology, and we're getting 8 little waveguides that can propagate the wave into the micro BGA. So essentially I'm going to talk through these 3 blocks. So we've got our commercially available dual converter, which is essentially 1 local oscillator split driving 4 mixers. We've got back-to-back amplifiers, image rejection, so we can facilitate complete, this could be up, up, down, down, up, down, down, up, fully configurable, gain control, oven stabilized, so we can have an IF of 16 kilohertz to 8 gigs, an RF of 8 to 32 gigs, inbuilt image rejection for the LO and this unwanted sideband, and the LO is completely tunable with low phase noise. So with the inbuilt heater, 0 drift. So essentially, this little box enables you to take any IF signal, up convert it to anywhere between 8 and 32 gigahertz with ultra low phase noise, and you can do with it what you want there. It could be a VNA extender or reflectometer or anything like that essentially. And that is available commercially. So the W-band, this is a bit more interesting here. So we won this project having not designed this W-band, just on the back of the performance we've got on the Ka-band extender. So we designed this W-band unit that is also available. We've essentially got a small module with an LO in of between 25 and 30 gigahertz. We amplify it, we double it, we amplify it, we filter it, we split it, driving 2 mixers. We got an LNA, so the mixers convert an IF of 20 to 27 gigahertz to 70 to 87 gigahertz. We've got an LNA, an MPA, a switch, and an output. We've got a target test path. So when they detect a fail on the tester, they can click in the target test path to check it's not a fail with the test setup, it's a genuine fail on the mimic they are testing. So we can go RF out, we can go RF in. We've got a VVA to adjust the gain control, low noise amplifier. There's actually some things that aren't shown here, like filters as well. We have small filters printed on the board, mixer, IF out, and that couples with our Ka-band module to make a fully configurable 2 to 6 gigs to 77, right up to 70 to 87 gigs. And you can actually use that as a network analyzer extender. Okay, so how we did it. So long lead times on these commercial available Rogers boards from certain companies that have been in the game for a long while. We couldn't tolerate the 16-week timescales and the extremely high costs. So we essentially designed this 2-layer 5880 carrier, had it made and bonded it ourselves to a gold-plated baseboard. We laser cut holes for the mimics and wire bonded them in. So the mimics that get hot are sitting directly on the gold carrier. wire bonded it with decoupling capacitors to the supporting circuitry, and we've got that same circuit that you see here is laid out on this module here. So essentially we've incorporated surface mount technology because these mixers and amplifiers are surface mount. We've done all the reflow and assembly in-house, all the wire bonding in-house, and it fully works. And so you can see we've got printed filters, all sorts of RF transitions. And normally when you pack something this close, especially at these frequencies, it just oscillates on the bench. And I'm going to talk about how we stop that oscillating as well. But just very quickly, we've had to do all the impedance matching. So if you just wire bond to a trace, you get pretty terrible return losses. If you do a matching circuit, which is all, we've modeled everything in ANSYS, you have induction, you have inductor, capacitor, 2 wire bonds. We can actually match it over the full band and we get really nice transitions from the dies to the chips. And even though we're sitting the die on the gold carrier, we've got silver epoxy, we've got bonding that we've done in-house that is passing the ground right where you need it under there with no mismatches or ripples in band. Okay, so on the back of the module, we've done all our DC bias circuitry. So we've got DC bias supplies with DC-DC converters that are inherently noisy, but we've got techniques to mitigate that. A microcontroller for controlling it, active temperature stabilization, so thermal oven. We've got all the amps require drain gate separate biasing. So we've got some clever circuits that bias those for minimal power dissipation, virtually nothing. And it's completely stable over temperature and manufacturer tolerances. So how have we shielded this thing? So without a cover, it oscillates. We do this in-house. This is a gold-plated top cover with printed absorber on it, conductive, and dispensed a gasket as a liquid. We do all this in-house and again offer it as a service to anybody who wants it. We're getting about 100 dB isolation between pockets, and it completely makes the whole module that is like this, all squashed together. It completely makes it behave like it's individual metal blocks connected by waveguide. It is very flat. And coming into here, we've got some the loopback measurements. This is actually a loopback test showing our 20 dB pad here, and we've got good conversion gain up and down. It correlates to the S parameter models exactly. When you couple it with our dual converter seen here, we've essentially got a two-stage VNA extender between 70 and 84 gigahertz. So what we've done in this experiment is we've got a known device here that operates at 86 gigahertz, and we've calibrated this system, and we've also calibrated a commercial VNA, and we're showing complete correlation. So this is a calibrated VNA versus our system, and we've got complete calibration on phase and magnitude. And essentially it just shows, it demonstrates that you can not only use this as an automated chip tester, but you can use this as a VNA extender as well. Okay, so the gasket and absorber dispensing, how we've done that, we essentially have got a dispense absorber. It's a liquid with the method and chemistry actually developed by us. So we've got a direct bond of the absorber to the metal. So by doing this, we are removing, normally when you get microwave absorber, it has a sticky layer on the back, and we lift the surface, stick it on, and that glue layer is actually a few tens of microns thick, and it offsets the absorber and the performance isn't as good. We've got a process now where we're doing a direct bond of the absorber to the metal, and you get much greater performance. So an example is we have a resonant cavity with coupling without the absorber. When we have the absorber, broadband, it just drops off. So, and we've now delivered over 10,000 of these modules to various customers. So definitely this stuff works. And we can dispense it in all your cavities in different shapes and sizes, different different places. You could be creative. This is our switch product, and we're actually dispensing it on the outside to stop coupling between our switch ports, and it suppresses those leakage modes. So we're obtaining something like 100 dB isolation inside this switch. The gasket stuff we're doing is we are dispensing a conductive gasket where we can do gaps for mouse holes where the RF trace passes through. We can print it different thicknesses, 0.6 millimeters all the way up to 2 millimeters. We can print it on edges, around connectors. This one here is this is a 100-watt radar unit that we got complete repeatable response over and flat radar power over 600 megs of bandwidth, and it's only with this absorber in the right place and the shielding that we can obtain that. And so again, and it can be compressed many times. So once you've compressed it, it works, and you could probably do it 20-30 times and maintain the RF performance. And again, it's a commercial service that we offer. So an example in one of our products of how we utilize this stuff, we've got a switch matrix in a rack form and a benchtop form. The typical loss and return loss is flat to 20 gigs and beyond, with a return loss way better than 10. We've got very high isolation, better than 100 across the band, and we've matched every single port path and port length to an extremely small amount where every path is pretty much almost identical. And so, and the whole thing's oven stabilized for zero drift. And we could never have achieved this without the absorber and the gasket, really, because everything is packed. I mean, inside this box here, there's 96 RF switches, and the whole thing is packed in extremely tight. And without the gasket and absorber, it just does not work. Okay, so let's talk about some real-world projects. So we've currently got the contract to test the new OneWeb payload by Ramon Space. It's a digital payload. I was previously 7 years ago involved in designing the first payload. So obviously that helped to obtain this contract because I really understand the payload and the way it's designed. But the digital payload, so our contract is not only providing design support and consultancy to the project, it's also doing all of the testing and qualification. And only now we're involved in we're involved in thermal vacuum campaign right now. So what we've supplied Ramon Space for this, so this payload, just to give you a bit of background, it's got 18 RF connections on it, 8 in, 1 out, 1 in, 8 out. It's KU, Ka band frequency converter with extremely wide bandwidths. I mean, we're talking 2 gigawatt, each band is 2 gigahertz wide. So this requires extremely high order extremely wide bandwidth modulation schemes, and it's got extremely high requirements for testing. So essentially, we've provided all the ground support and we're conducting the tests. So just to show you how we've set up a tester here. So this might be of use for you if you've got big payloads, big projects, big RF port count devices. How do you test them? And you might employ mechanical switches, you might employ all that kind of stuff, but the mechanical switches are expensive. They don't go quite back the same way. Our switches are low loss, oven stabilized, and we've shown that we can fully calibrate a VNA for S11 measurements completely through them. So essentially, the payload, we've got our kit set up here. We've got a VNA connecting to our full crossbar switch matrix. We've got a low frequency. So there's a customer requirement to measure EVM of the signal under modulated data. That's actually really expensive to do at Ka band because the signal generator is very expensive. It's also very expensive to do a demod at that frequency. So what we've opted for is using our frequency converter to mix it up and mix it back down again. So we've got a full crossbar matrix. So that's any to any, which is ours, VNA connected to it, the low frequency modulator, lower cost, with our converter connected to the switch matrix. We've got a low frequency demodulator and our converter connected to the switch matrix and 16 DUT ports. And we can essentially automate the whole process. And this is actually a demod through our system of a 125 megahertz bandwidth signal, and we've got an EVM of 34. which is extremely good. And that's actually coming from a 2 gigahertz input signal being mixed up to 14 gigahertz through the switch, back down, and all the way back down again. And so essentially we've demonstrated here that you can get the same measurement quality as you can when you buy the bigger, higher frequency instruments. So if you already have lower frequency kit, you can extend its use. And finally, I'm going to wrap up. This is our TVAC campaign we're undergoing. So we've got the OneWeb payload inside here. We've got all our kit set up. We've got the payload about to be, this was taken on Monday, about to be pumped down into vacuum. And the whole test setup is configured to test all 18 ports continuously at the same time. Okay, so just to sum up, really automated test, and design of these small compact modules, it's all very easy to get them repeatable, productionizable, consistent with the right techniques. And so we offer consultancy, we offer lab support if you need any of our equipment, and we also offer the products as well. So, and we'd be happy to partner with various companies. So yeah, so if you any questions.
Thank you very much, Ben. I can't believe how much you crammed into that presentation.
No, it's a lot. It's a lot. Sorry.
Liam, you've got a question.
I have. Thanks, Ben. That was great. It's great to see this sort of kit being designed and manufactured in the UK. So my question is, in days gone by, when people built stuff for space, they had to use space qualified components,
Yes.
which generally meant A, they cost a fortune,
Yes.
and B, the technology was about 10
Yes.
years old.
Yes.
Now, I realize this has moved on a lot. Could you give us an outline of your approach for developing kit that goes into space?
Yeah, well, it is
specifically when you do the
difficult.
components?
The ground kit is obviously you can choose anything, but for the space stuff, if we take our low noise block that we supplied to the US Data Center and Space Company, that's gone up last week, you can't use completely any commercial component. So where we can do, we've used components that we radiation tested, where they have, you still might be able to use them with a fail, but you need to mitigate those failures. For example, we monitor the current, say on a phase-out loop, and we know the upset rate might be 1 upset per week, per day. But the upset is a latch up. It could short the power supply and kill the device. So what we do is we mitigate that. We use, for example, a current switch limiter to monitor the current, turn off within, say, 100 nanoseconds and reboot the device. But then that brings into question, again, the current switch limiter might be a commercial device. Can we use it? We radiation tested it, found the current switch limiter bit works, but the reset flag trips continuously. So again, we had to mitigate that. And so we use an RC filter to show that any blip doesn't pass through, but any genuine latch up does. So you've got to design, you can design the hardware using commercially available components, but you must mitigate any effects. So you might go ahead and buy a rad hard component. It might be £5,000 for a DC-DC converter. Again, you can use commercial ones if you mitigate it. And again, it depends on the quality level and the quality assurance level you are looking at, because testing costs money and testing is very expensive. So it depends on the volume. And so ultimately it's still expensive to do space electronics. The LMB we supplied for X-band that's gone up now is not just throw everything in it. Every single component is carefully chosen. The thermals are carefully chosen because we've got to design for vacuum, and so we've done mechanical vibration testing, and we've done all the testing on it to give it the highest chance of success in flight. But really, it's heritage. It's knowing how the device performs in space, and even if it has a defect, doesn't mean you can't use it, but you must mitigate it. And yeah, that's why space is expensive and takes longer.
Great, thanks.